This is part 2 of using single-cell fluorescence to track phytoplankton communities in the ocean, an interview with Micky, Myrick, and Tammi Richardson of the University of South Carolina. To hear about how their systems work and the results they've seen so far, please listen to part 1.
You've alluded then to some of the kinds of things you can come to understand about the phytoplankton through these studies. Could you give me an example then of what would be something you've learned in terms of the ecology of the phytoplankton or their impact on the environment that these kinds of studies could possibly reveal? Like, for example, I think you even mentioned the difference between phytoplankton species that sequester carbon and those that don't.
The bottom line, I guess, is that instruments that can give us information on phytoplankton community composition, how it varies in space and time in the ocean, is incredibly valuable to studies of ocean ecology. All phytoplankton will take up carbon, and one of the things, so from the actual instrument development point of view, we've certainly reached the point that we can see different phytoplankton types in the ocean. They vary with respect to shape and size and pigmentation, luckily for us, because that's the characteristic that we exploit in making these MOEs. But in general, big return on this is going to be when we can get these MOEs incorporated into instruments that will sit and sample in the ocean or move around and sample in the ocean, and that would require teaming them up with some kind of small submarine. But the idea is these would give us any information we can get on phytoplankton community composition, how it varies in space and time, has some really practical applications. One of the tools, for example, that we could use this type of instrument with would be monitoring for algal types of phytoplankton that are potentially harmful. And there's a lot of different phytoplankton cells that make toxins. We call these harmful algal bloom-forming phytoplankton. So this is the one application that could be incredibly useful, not only from an ecological point of view, but from a public health point of view, is to have a set of MOEs that code for a particular organism that we know makes a toxin. And that's one practical example. So I guess the bottom line, getting back to your question, is there's no direct ecological information that we've pulled out of making these MOEs yet, but the more MOE sets we make and the more progress we make in terms of perfecting all the algorithms that go into relating the information that we get from those MOEs to what's really in the water, in the long term, that's really what's of interest to us.
Wow. So what are your next steps in this work?
Well, we'll continue making filter sets for as many different varieties, shapes, sizes, and colors of phytoplankton as we can. I guess Micky's group will continue working on the algorithms that convert the information we get from the IMOC instrument to something that I understand personally in terms of phytoplankton community composition. I guess down the road, a future step would be reducing the size. The instrument that we use right now that incorporates the MOEs is about the size of a small table, and the idea in the future would be to reduce that smaller and smaller and smaller so that it would fit on one of these autonomous underwater vehicles that are commercially available. I'll make it clear we're not in that business, but we definitely are interested in being in the business of making some of the sensors that go on these packages again, small submarines, moorings, it could sit on a dock. It really doesn't matter to us. The idea is to make these instruments that can go into the water and give us a bigger picture of what's happening in the ocean in terms of phytoplankton community composition. Micky, did you want to add any future steps?
Yeah, actually, there's a couple of things that are on my mind right now for the next immediate future. And the first of those is trying to understand how to take the data that we're getting and extract or tease out of that as much information as possible about those natural systems, about the phytoplankton that we're seeing and their health and the nutrient conditions that they're living in and so forth. And that plays back into the question of how you design the optical elements. And it's a big, complicated problem from, maybe that means I'm not seeing it very clearly at the moment, but that's how I'm thinking about it right now. It's a very complicated problem with some sophisticated data analysis tools that we need to begin applying to those data. And the second thing is, of course, we're not the first people to make an instrument with the intention of understanding what phytoplankton are in the ocean. One of our collaborators is Heidi Sosik at Woods Hole in Massachusetts, and she has for more than a decade been working on an instrument called the Flow Cytobot, which is, you can go online and see real data from that instrument streaming out every minute of the day for months at a time. It's sitting out in Martha's Vineyard and recording pictures of phytoplankton as they float past, all different sizes and shapes, and she does classification of those. And one of the things that we would like to know is, how does the data we get relate to the data that she gets? But she gets beautiful. I mean, you should really see these things. They're just awesome pictures of these cells as they pass through her instruments. She's got pictures of them, but not the pigment breakdown of them. We get something more like a pigment analysis, and we need to figure out how to mate these two pieces of data together. We see them as complementary pieces of information, rather than, our instrument's better than that instrument, or their instrument's better than ours. It's really they get information we don't get, and we get information they don't get, and we would like to be able to synthesize something new out of the two things together. So that's what I see as big steps for us.
Yeah, and I think Micky makes a very important point. We're not trying to recreate the wheel. We're trying to recreate, or maybe produce, something that makes the wheel even better. And an important difference between the Flow Cytobot and what we're trying to do is, again, it gets beautifully detailed, wonderful pictures of phytoplankton in the ocean, and we, couldn't hope to achieve as good of the optics as they have. But they also have the requirement that flow, it's basically an underwater flow cytometer. That instrument needs to be cabled to the coast. It needs to be plugged in. And so we see what we're developing as something that doesn't need to be plugged in, could run fairly long on a standard battery, and that would give higher resolution pictures of what's happening in the ocean in terms of community composition. If you can picture the flow cytometer sitting on the bottom of the ocean and an IMOC instrument flying around it, and I do mean flying as in flying like a submarine, flying around, getting more detailed, different information that complements very nicely the information that Heidi's taking from that fixed point in space. And we should mention also that her collaborator at Woods Hole Oceanographic Institution is Rob Olson, who he and Heidi have been has made some fantastic advances in the last few years in terms of this type of technology.
Well, fantastic. Tammi and Micky, thank you so much for talking to us today.
Great, we appreciate it.
Thanks for having us.